So I will be speaking in English because my Polish is not that good to do a presentation, but yeah. So I wanted to talk about game optimization and various tips and tricks about that because it's my pain. I have been optimizing a bunch of stuff in a bunch of games, so I think it's just important for me and important for me to talk about. Yeah, so I prepared the presentation, but have not prepared the talk, so let's see how it goes. Yeah. So about me, my name is Kirill, or a nickname Xorboo. You can find me anywhere with that. I've been for about 10 years making games and recently switched to some enterprise VR stuff. So not gaming, I'm a trader, but still I have a bunch of games that was released. Some of them weren't released, and a lot of them were cancelled that I can't even talk about. I've been making games for PC, I've been making games for mobiles, I've been making games for WebGL, and on a bunch of engines as well. Mostly Unity, but also Unreal Engine with VR a little bit, Default, and Cocos 2DX for with C++. I've also made a game for this thing on last Hack Jam. Yeah, so I've been working with lots of engines, and there are lots of common stuff that we can optimize in games in each of them, and I'll just try to combine it all so that it's in one place that everyone can look at and just get some knowledge. Yeah, and like one of the stuff, for example, my first project on Unity was where they just throw me a game that should have been released 4 months ago, but just small team got disbanded, and they asked me to optimize it because the game was ready, but it was just crashing on iPad 2, I think, on the target device on startup, and I had to make it work. And yeah, that was my first time with Unity. It was fun. Yeah, so why do we even care about that? Why do we optimize the games in general? First of all, it's of course a bad player experience. If players can't play the game normally, if it lags, if it takes a lot of space on their hard drives that they can't install, or they have to download like 50 gigabyte patch on a mobile connection because that's what they have, it's a problem. And it often leads to bad reviews, and so it leads to lower income for you, so it's anyway bad. Also, there are lots of requirements for consoles and VR. For example, it has to have a stable frames per second, or it has to have some special other cases, and you have to think about that and you have to plan about it. Also, you just often limit the amount of devices that would support your game. So, for example, only players with RTX video cards can play it. It's a problem because there are not so many of them at this point. And also even the build size matters, especially on web and mobile. So there was a talk about where they checked a build size and compared how many players did not even download it. And you can see that in Egypt, even like 40% of players can drop on a 10 megabytes game for WebGL because they have slow connection. They often must pay for per megabyte. It's not unlimited connection. So it's a problem for them. They just drop and they won't even play your game. But of course, it's not that important for consoles and PC because everyone has problems now. But still, not everyone actually. So when do we want to optimize? Well, there is a known quote, you probably know about that, by Donald Knuth. Premature optimization is the root of all evil, because you usually don't want to optimize on the start. You don't want to optimize immediately. Especially in games, you have to prototype, and so you always want to move fast and optimize only when it's actually essential and required. You also don't want to optimize on game jams because you don't have time for that. Unless there is some specific case that you must do and you can't live without it. But usually just drop the stuff and do something else. Also, first of all, you have to profile your game. You have to know how to do that in all of the terms, like how much time does it take to render, how much memory does it take, why are there lag spikes at certain points, and all that. And because usually you want to optimize something like, oh, hey, I can use like hash sets here or something else, but usually you will save nanoseconds in this place, where instead you could save a lot of time in other places. And of course, if you don't have a way to measure something, you don't see that something has improved after your optimization, it's basically you've wasted your time that you could have spent actually making the game. And just the standard 80-20 rule, because usually some specific optimization will do most of the stuff that you need, and you can ignore everything else. And also, you don't have to optimize all of the time. There are cases where it's just good enough for players, so it's good enough for you. For example, here is a game from Mario from the 90s, and they have some terrible code that I've just stumbled upon on Twitter recently, where they spent like 15% of the whole CPU time to render player score on top. It was mostly because they had to re-render it on every frame, they didn't cache it, and because like it's stored internally and converted to digits on screen every time. So it was terrible, but it works for them, it gives them what they wanted, and that was enough. And it's often enough for you as well. So we come to question, what exactly do we want to optimize and when? So first of all, some things you do have to think about in advance. First of all, in production, you wanted to know like where are you deploying? Are you making a mobile game or are you making a VR game? Because on VR you want to have at least 72 frames per second because that's the standard for Quest 2, but now you probably even want to go to 120 because it just reduces, for example, motion sickness there. On mobile, you care about player's battery because you just get 1-star reviews because it drained my battery in 10 minutes and all that. On PC, you just have to think about the minimal target device because there are lots of players. You can think about which, well, like all this graphics card do you want to support and stuff like that. Then you think about architecture after you know that. You know the limits of your platform. You know that on WebGL, for example, you usually only have one thread, so you can't parallelize stuff. So it may be limiting to what you actually can do there. You also, especially in AAA, you want to know the budgets for each. For example, if you want to go 60 frames per second for a PC game, then you know you have 16 milliseconds for each frame. And that's maximum what you can do, apart from maybe special cases on maybe when something is loading and all that. And in AAA, often when there are certain departments, like one is doing shaders and graphics, another one is doing AI, they often just can limit like, hey, you have like 5 milliseconds of CPU to do AI stuff, you have 8 milliseconds to do all the rendering, then we have some extra stuff for something else, and you have to know that that's your limit, and you have to check that you're keeping within it. And during development, there are, again, optimizations everywhere. It's not just code, it's also in resource management. What do you load, how do you load stuff, the graphics, of course, the animations, AI, it's everywhere. Now, how to profile, because, well, profiling is important. The easiest thing is built-in tools in engine. It's, for example, Unity and Unreal Engine. It usually is enough for 90% of the stuff. You can see how much CPU is used, how much GPU is used. You can also check how much memory is used, even like when allocations happen and all that. And you have to familiarize yourself at least a little bit with that to be able to see what causes the problems and when, because it's actually, once you know the tool, it's fast to just quickly open it, check it, and that's all. Sometimes you can just add custom timers in code, in shaders as well. Often when you just select a special part of the code that you want to profile, you compare, check how many time it takes to execute, then you try to optimize, you check it again, and just and on and on. But sometimes optimizing an editor is dangerous, especially like on later stages, because it's not the target device. Even if you're still releasing on PC, it is running differently. Engine itself causes a lot of overhead, especially like in Unity. There are lots of editor stuff that runs, and when you look in profile, you can see that there are lots of garbage added on each frame, which only happens in editor and won't happen in your release game, and you will just waste your time trying to optimize that. So there are lots of standalone tools that you can use, but it's very specific, like for graphics, for specific device, and stuff like that. And often you can also attach editor to a target device, so you just connect your phone with to your PC, you run profiler, but actual game runs on mobile, so it's more stable and you can actually see a lot of stuff that you wouldn't be able to see in editor. Yeah, and also it's sometimes worth to try to set up some continuous deployment, so you just do some automated tests, you run editor, you run some scene, you wait for 1 second, you check what's the frame per second value, you record it, and then you can see, oh, okay, in this pull request something broke and we are much slower, so we should go and fix it. And it's easier to track that way, but it's sometimes hard to implement if you're indie making some small game, but it's still not as hard as it may look like. So it's worth looking into that. Now I will talk about separate parts that I can think about. So first of all, it's size of the build of the game and everything like that, and how can you optimize it. First of all, textures. This is the thing that takes most of the memory in most of the games, especially on mobile, and you usually want to optimize that. You don't want 4K textures on a mobile phone because no one really has 4K screens, and especially if your texture will take only 10% of that screen. So you have to optimize it. Engines are not that smart, they often will keep them full size. So you have to either set in an engine, or ARSys should provide you with appropriate size from Photoshop or whatever. You can also use lossy formats. There are special formats for Android, for iOS that you can use, which take less size per pixel for each texture, but it may cause lots of problems. So be careful about that, about where do you apply it and where do you not apply it. For example, UI with gradients, it's usually hard to do something like that. Then it's just often you can do a small main build, which is like especially for devices, mobile devices, and for WebGL, and then a lot additional resources in runtime from your server, from some CDN. In Unity, it's called asset bundles. In Engine, it's pack files. So you just, when you build the game, you build it in separate resources, you upload them to your server, and then the player will download it only when necessary. For example, a group of levels, or like in Monster Hunter now, like it's a new Pokemon Go, for example, when you meet a new monster, it just starts loading all the animations and models for that monster, so you have to wait once, but then it is cached on your device. So this is useful because even like especially initial build size can also deter players from downloading it, even because if they see that it takes like 2 gigabytes, they will skip it and try to find some other game. So yeah, that's what you can do. So download levels, download extra graphics, maybe 4K textures that can be optional that player can select to download. That sometimes happens on Steam. Lots of stuff like that. And also, for example, this is a build report from Unity. When you run a build, you can just go into the editor log file, and you can see a list of like files that it got baked into the build and how much space do they take. So you can often see that you see some textures that take 16 megabytes, and you understand that you don't want this texture to be 16 megabytes. You just by accident forgot to reduce its size. So it's also sometimes useful to just keep track of it from time to time. Now also about load times. So there is like a simple graph. You know that CPU speed increases quite fast, but disk speeds do not increase. We have SSD, we have NVMe SSDs, but still it does not grow as fast as CPUs, and we have to play around that. And that's why we try to load stuff at runtime and not on initial load, because players don't want to wait 1 minute for the game to load, especially if they don't have SSDs. There are still a lot of people like that. And also, if you can manage to load only part of the stuff and then unload it when you don't need it anymore, it also saves you in RAM, because it's also can also be limited. And you can also often customize it based on device. For example, you can have 2 packs on player's hard drive, but you can load lower resolution textures on a weaker device, so it's easier for them to run there. And also asynchronous stand loading is just Unity and Unreal Engine. There are two cases. You can just load levels dynamically and then load them, and it tracks it more or less well. So it does not. You don't have to load everything. You only need to load what the player will see next and where the player is right now. Yep, and the same with resource loading, asset bundles, and pack files, plus frunnable, which is running the load of that pack file in separate thread, which is what we did at some point, but I'm sure there are probably some other cases as well. Also, you don't often have to actually reduce the time of load screens. You can often fake it. For example, here, like in Bayonetta, there is a loading screen where you can actually play with your joystick, you can practice your moves, but at that time the game is actually it's loading a large level, which takes time on consoles, and the player does not feel it because he can just run around. And you can see that often in lots of games, like in Assassin's Creed, where you just walk in some fog in like VR games as well, because there are strict limitations, because player can't just see a static black screen in VR. So you often can just play around that. You don't have to actually reduce everything to a minimum. The second type of optimizations is what I call common sense optimizations, which is just stuff that triggers me a lot, because there are like stupid mistakes which could be avoided, and it's not even harder to implement. It does not take time, but it just happens. Often it comes from developers not knowing the engine too well and doing stuff that they think is fine, but actually is not. So this page is about that game that was crashing on iPad, basically. So first of all, they were scaling an object to 0 instead of disabling it. So imagine there were like huge 3D animated buttons of level groups, and they just scale them to 0 with particles, with sounds, with all the animations, and they just scale it to 0 because it doesn't work like that. If you don't see a problem, it doesn't mean it's not there. And also, sometimes when some objects are behind the player or too far away from the player, they're still executing. They might not render if they're not in camera view, but there are still scripts that are running, like particles are running and computing the location. So sometimes you see that something is really heavy on CPU, you can just optimize it, think about it. If player is far away or player is not looking in the direction, you can just disable it and you enable it back when needed. In Unity, you have to think about that. There are prefabs that you just drag around on your scene, on your other objects, on components, and you have to remember that each prefab, even if you don't instantiate it on the scene, it still takes memory. So often there was like a huge game manager class with all of the levels which were prefabs, and they actually all got loaded, and every texture in them got loaded, and it just was out of memory on iPad, and it crashed. That's why you have all those asset bundles and dynamic resource loading approaches. And just remember that the most important thing that you have in every game is just spawning objects is expensive, because engine has to allocate the memories somewhere, remember the IDs, and do a lot of other stuff, and it takes a lot of time. So you want to minimize that in one way or another, and I'll talk about that later. Also, try not to check for something in every frame if it only happens once at some point. Use events. There are Unity events internal. You can just use language because C++ provides way to call something. Unreal Engine provides its own way to call something. Just invoke events, broadcast events, call some script specifically. Don't check for a Boolean value in 100 enemies every frame if you can just get an event for it. It also takes time. Now to code. Again, profile first. It's often not the code itself, it's not your script, but it's usually graphics or some special cases that you have forgotten about. And don't over-engineer stuff, especially early. If you've studied an IT and you got an IT degree, you know about big O notation, and I think it's extremely overrated for game development, at least in 90% of the cases. Because you know that, okay, if I know that algorithm is faster, okay, but if you have an array of 10 elements, you don't care about how do you sort it. 10 elements will sort with any algorithm fast enough, and sometimes there are complex algorithms. They use complex data structures which take time to allocate, which is not considered in big O. So again, profile, see if it's actually bad or not, and then optimize. But you still have to remember about special like game dev algorithms. It's case-by-case basis. I just mentioned a few. So A star is a search algorithm on the grid, which is really useful. You don't just want to flat fill or do something like that. And quad tree is a way to specialize the area and group objects around. Now about garbage collection. This is mostly for C#, but it's still important to understand that what happens. And main thing to know about is stack versus heap. So in managed languages like C#, when you create an object with new, it's just allocated on the heap. And at some point, when you forget about this object, the garbage collector will just randomly kick in at random point in time. It will freeze your whole game. It will take some time to check what should be cleaned. It will clean it, and then it will unfreeze your game. So this is what often happens with lag spikes, where everything works fine, but every 2 seconds you just see a small frame drop, which you might not even visualize if you just show a frames per second value in the corner, because it just drops from 60 to 59, but actually it took like 200 milliseconds to render current frame. And you have to try to minimize that in one way or another. So also just know about class versus struct. Struct allocates on stack usually, class is what causes problems. So yeah, it's expensive, and yeah, so especially it's critical for low-tier devices, for mobile, because on mobile it takes even longer. On PC it's more or less fine. Also in Unity, there is also, I think it's 2 years old already, but they've optimized their garbage collection so it doesn't take one frame. It tries to separate it in multiple frames, so it's not that bad for your game, but it's still hard. So what exactly would you want to optimize? First of all, again, optimize only what's important. If you create one array once on loads of the game and you just use it once and forget about it, it's fine. But if you do something on every frame, that's when you should try to think about that. So try to reuse arrays. Don't create a new array, temporary array to do something. Just create a single array, use it, then just reuse it again and again. Also, arrays are dynamic, so each time when you will keep adding elements. At some point, it will have to resize, so it will have to allocate again. Also, avoid using strings as much as possible. Don't use strings as game object IDs for your stuff. Try to use integers or something like that, and use string builders if you must do something with strings in general. Yeah, also know your engine. In Unity especially, there are lots of stuff related to physics that allocate. So when you do array cast or something, it will return you an array. And if it returns you an array, it created a new array and it allocated memory. Often there are non-alloc variants of the same method, so you can again reuse the array. If you do array cast every frame, just keep an array in the component and pass it to arraycast, check what values are there, and forget about it. Yeah, and also there are like best practices from Unity. I'll share the presentation in the end. You can download it and click on all the links if you care about it. Now, the most important trick of optimization for garbage collection is object pooling. And it's not just for garbage collection, but for spawning objects and creating objects in general, which is like the slowest thing in engines and the thing that you have to do most often. You spawn bullets, you spawn enemies, you spawn lots of stuff, and it's expensive. So what do we do instead? The usual case is we just create a bullet. When it hits something, we destroy it. We destroy the object, it's gone, and then we create a new one. With object pooling, we create a bullet, then instead of destroying it, we just keep it in some queue or array. We disable the object, of course, we just keep it in the queue, And then when we need to spawn another one, we just grab this object again. And it does not allocate memory, it does not cause a slowdown, and it's really helpful in a lot of stuff like that. So when do you have to think about it? Mainly when you do something each frame. That's like that's what should trigger your brain to think about optimizing. So it avoids heap allocations and yeah. So bullets, like some collision effects when you spawn particle effects, but keep in mind that you have to wait. You need a way to reset the state. For example, particles, they spawn in some state, then you disable the object. When you enable it again, they may have already been spawned, so you need to call some method to reset the particles so they start emitting from scratch. Yep, and in Unity they have some own Unity engine.pool. I did not find anything for Unreal for this case, but often you can implement it yourself. It's really easy, it's just one class. You can even make it singleton, I wouldn't mind, with just two methods and an array, and that's it. Yeah. Now let's get to general CPU usage, which is also a problem for most of the games, because you know there is like one thread that runs the whole game, and every other thread in our 16-core CPUs doing nothing. And you have to try to use it in some cases because engines are incredibly bad at it. You know that lots of stuff you can only run on main threads, like usually engine-related stuff, like spawning objects, using some affecting physics and all that, because otherwise it would cause problems. But you still can do asynchronous loading. You can load resources asynchronously in other threads, and you can just simply run every hard task in the thread. For example, AI. If you have to you need to do some hard pathfinding, you can just run it on some separate thread. Then once it's done, maybe even like half a second later, you check it in game thread, and then the agent starts moving. Because you often don't care that the AI will start move immediately. It can just stay in idle animation for half a second and then go where it should go. Yeah, so about like those CPU heavy tasks. At first you might want to use coroutines, which again all engines, but you should note that usually they just run on main game thread. It's just a way to slice the execution logic into multiple frames or with delays. So you still slow down. It's okay for lots of stuff which is not actually heavy, but you just want to have the delays in a single place. But you need to use some other stuff if you want to run it on separate thread. How to do that? Yeah, usually like there are cases for Unity for Unreal. In Unreal, it's really quite easy. I think you just use async task and you just spawn with frunnable on a separate thread, and then you just call it to run some callback on a game thread, and that's when you know you got the results, you got your data, and that's it. In Unity, you can use async await instead of coroutines. It's like this similar to just regular C#. It's almost the same, and there you can actually easily go to some background thread, do some stuff, then await and go back to main thread and, for example, compute something and then display it in the UI on main thread. So it's actually not that hard once you just find some examples with that, and that's it. And also, as really special case, you usually won't use it, but there are compute shaders. There is a way to execute stuff which is not directly related to graphics on GPUs. Because if your GPU is underused, there are stuff like fluid simulation or something that you can really parallelize by a lot, like when you have a huge array and you know that each element has to do something independently of each other. You can try to use compute shaders for that. You just set up the data, pass it to GPU, wait for it to compute, and then get the results and do whatever you want with them. And now to random access memory. So you remember this graphics, and it's the same with RAM as well. It's slower than the CPU. There are some problems with that, but there are some cases that you should care about. So it's slow, and main thing you probably will hear are cache misses. Because there is RAM and there is cache closer to CPU, which is small, like measured in kilobytes or maybe megabytes in some rare cases. And when you try to access something like anything in random access memory, like an element of an array or something, if it's not in the cache, you get a cache miss. CPU goes to RAM, but it does not get just this element. It gets a so-called page, which is like 64 bytes, I think, of data or more. I might be mistaken, and it takes all of this data around your element, so from your element and forward, like how page is located, and it loads it all in the cache. So why it's good? For example, if you have an array, you load first element, you get cache miss because you have not accessed it before. It loads the whole page into cache, and when you get the second element, it's still in the cache because it's near the same location. So then you don't get cache miss for a certain amount of time, and then you get another cache miss, but it's still optimized in that way. That's why I've told that some complex data structures are bad. It's just because lots of structures are allocated on the heap, like trees, unless it's a binary tree as an array, but still, and it causes a cache miss on every time, and it just slows down on something that has like thousands of elements. And that's how we come to entity component system, which is a way to avoid those cache misses and like to make the code faster. It's just a separate approach to how you of architecturing your game. So instead of like just object-oriented programming, even similar, it's so-called data-driven architecture, where each entity, for example, you can think about as an enemy or player or something, and component, it's the same as component in Unreal or Unity, but instead of storing each component next to the object that owns those components, the actual data is stored in arrays like that. So each array is for a specific component type, and it stores the data for all of the objects. It's a simplified way, but still. And in this case, when update happens, which happens on every frame, instead of updating an entity, so updating each component of an entity, a whole component is updated. So for example, a movement component is updated, then an AI component is updated, and so on. It has some complications. It's sometimes hard to wrap your head around how to work with that, but it can be much faster, but it depends if you should use it or you should not use it, because it's not always when you need it. If you have 10 enemies, again, it's 10 components, you don't care about that too much. But if you have like Vampire Survivors, where you have 200 enemies, which is basically bullets, you probably want something like that, because it will be noticeably faster, especially on slower devices. Yeah, and there is again a link. There is it's not even a talk. It's a series of lectures on game programming, and again you can click the link later. And there, the Dave describes a way to implement ECS, or teaches students to implement ECS in a simple way, so you can just actually think about how it's implemented and not just use it in Unity or wherever, because it's often good to understand. And I found this quite easy to listen and to understand. Now, physics. How do you deal with physics? Because unless you have a specifically like hard physics game where you have some like, I don't know. Anyway, first of all, try to fake it. You don't need physics, and a lot of the times you can just fake it. You don't need to built-in engine physics. You can just fake gravity, fake bounce, and it would be enough for a lot of games. For Unity specifically, there is so-called collision matrix, which is where you set which layer collides with which one. So you can often set that, okay, there are enemies, there are projectiles, they collide with each other, but projectiles will not collide with water, will not collide with trees or something like that. So it's just faster. The engine won't have to think so much about when it calculates the physics. And just when you use colliders, in Unity specifically, avoid mesh collider, but your collider does not have to match the actual object, because object may have 100,000 triangles, but as a collider it can just be a box, because that's enough for you. You don't care about every little detail there. And now the hardest part, the 3D graphics. Sadly, there are lots of stuff, again, on case-by-case basis, and it's hard to know what you have to implement and when, so I'll just go about some small tricks that I know about, and maybe you will remember them when you need them. So there is like a pipeline of the graphics where you go from a vertex processor, where you have a mesh, you have triangles in that mesh, and you pass it to GPU. It splits those triangles. It goes for each triangle. It rasterizes it on the screen, so it knows which pixel contains which triangle. Then it actually processes them each fragment, so it knows which color it should be on the screen, and then it outputs it and shows it finally to the player. So you have to know about that. Everything is expensive here, like huge meshes are expensive, complex materials are expensive, shaders, animations are expensive, and you usually have to know lots of stuff about that, but it's still good to look into that in Profiler and try to optimize it. So first of all, like passing data from CPU to GPU. Now, this example in particular is not related to that. I guess it was because they just were limited by memory and they didn't even have proper GPU back then. But in Mario, you can often notice that grass and clouds are actually the exact same sprites, simply colored differently. Because you can just optimize it this way. You don't have to pass two textures to GPU every frame. You instead can pass just a single texture. And that's where we come to the most important term that you should know about. It's a draw call, which is on every frame you send a bunch of commands to GPU to render some stuff, like render me this object, render me player's hair, render me player's glasses, a gun, a bunch of explosions, and each call would be a draw call, and it affects the state which GPU has to do the actual render. And doing the draw call is expensive. Of course, it's not that expensive, but still, again, case-by-case basis, but sometimes on slow devices, you're limited by 1,000 draw calls per frame. On fast computers, maybe more, but still you have to think about it. How do we optimize it? First thing is GPU instancing, which is supported on most modern GPU, not just RTX, but for the past maybe 10 years or so. Which is where you can render lots of meshes, the same materials in a single call. So basically what you do, you pass a list of locations of transformations, so where the object is, how it's rotated, how it is scaled, maybe some additional parameters, and you pass an array of this for like 10,000 bushes that the player can see in the forest, and it renders them all at once, and it's much faster than rendering each separate one by one. An easier way is so-called batching. It's combining multiple meshes into one. It can be done automatically, and Unity does that, Unreal does that, but you can also do that manually. Usually you do that for objects that use the same material. So for example, you have multiple houses, maybe a few barrels which use the same texture, the same rendering material, and you can often batch them together. So they again using one draw call, sending that to GPU, and it's faster than drawing each one separately. There is static batching. So for static objects, they don't move, they don't change their style, their shaders. You can often just do it statically. Just as post-process, for example, your level designer put 10 barrels around the house, and as post-process automatically often, you can just combine them all in a single mesh and draw them as a single mesh once, and that will be faster. And dynamic object for moving objects, for like any non-static objects. But here on every frame, CPU has to think about what can it optimize. It will think about what can it optimize fast, and so it will take time from your CPU. So if you want dynamic batching, think about if you are GPU bound or CPU bound, because sometimes it may even slow down your game. And also just texture atlases, which is combining multiple textures in a single huge texture, passing it once, because then you can reuse the same texture on multiple meshes and you can batch them together. Another way to optimize is culling. Basically, you don't need to render every object. Often you can help GPU ignore some of the objects that player doesn't see. Most common one is frustum culling, because camera has a view frustum, and engines do that automatically. They don't pass to graphics card whatever is behind the player. So that's easy, you usually don't have to think about it, but often, for example, if you have like a huge level with walls and everything, and you bake it as a single mesh, you can't custom call it, so the whole level will be rendered every time, even though the player is in a specific room, only sees like 6 walls, and that's it, but everything else will also get to GPU and will have to be processed. So think about it, sometimes you don't have to combine everything, sometimes you even have to split it. And then occlusion culling. Occlusion culling is a way to hide objects that are in player's view but are behind other objects. This is also can be done statically for all static objects, which ends up that engine computes it, and then it knows that for any location where player can be, it knows which objects it should render and shouldn't. So it loads it into memory, and then it just every frame it gets it and it checks which objects it should enable or disable. But there are problems because it may cause glitches, because it does not take like for every centimeter, or it takes like spatially. And like, for example, here in Escape from Tarkov, you can see that in some special area, which is not easily accessible, but still you can just hide those crates. And if the player is inside those crates, you will see him. And you can even wallbang him, so it's a problem. So you have to be careful about that. Now, the vertex processor, which is like, again, the main thing here, if we have passed something, the main problem is having a lot of polygons. So here is like a problem from City Skyline 2, which was a few months ago. It's a strategy city builder game, but you have some player models there, like just humans walking around on the street, and the actual mesh that got passed there contains all the T's, and it was a huge problem for them. There were arguments about that they used AI to generate those models and they did not optimize them, and yeah, it caused a huge problem for them, so you have to be careful about that. It's again based on gameplay. In this case, they did not need T's at all. No one will ever look at those, but in like first-person shooter, you will have that. So think about what the player will see up close and what will see from the distance. In Unreal Engine, you might have heard about Nanite, which is a new way to work with that. Like, you don't care about this at all. You just have your ultra specific mesh, you pass it, and then the engine takes care about it, only loading it in a specific quality. But for now, it's really only for RTX video cards, and even then it barely works. So it's really, I would not recommend it to use right now, still think about it, but maybe in 5 or 10 years we can forget about this slide entirely. And another most common approach is level of detail. So again, you saw this huge mesh here, and instead, why don't we have 5 meshes of different quality, and instead just pass the lowest quality that player wouldn't notice. So here is probably not very well seen, but just a screenshot from Wikipedia, where there is a sphere with lots of triangles, but if player's camera moves far away from there, you can just roll it, like decrease the amount of triangles by like 1,000 times at least, and player won't notice at all. It's a slight CPU overhead because you have to compute the distance from camera to the object every frame or every few frames, but still it's often much better. Again, there are automatic stuff like Simplygon and other plugins that will do that, or you can just ask your 3D artist to draw smaller models. It sometimes will be better. It may also cause artifacts. For example, in first-person shooter, you can see some breach 1 kilometer away, but you have a sniper rifle, you zoom in. If developers did not update level of detail, you will see this low-quality breach when you zoom in, and it will be not that well. Yeah, and the ultimate load is billboards, which is basically a sprite or a few sprites as a final way to render an object. You don't need a complex mesh for each grass there. Instead, you can just throw 3 billboards and it will be good enough, especially on longer distances. And the last way is often you don't need a lot of quality in the mesh. You instead can do that later in fragments shader. So the most important thing here is normal map. So you have a separate texture like this, and it just shows the direction of the surface in each specific pixel. which is then processed for lighting effects, for shadows. You'd actually, like, here is the mesh without normal map, is just a flat plane, like, well, rotated plane, and here is with normal map added. It's still the same number of triangles. It has to read from an extra texture, so it does take a bit more time, and it's a more complicated shader, but still it's much faster. It's used almost everywhere forever, and try to think about that. Now to rasterizer. Again, if you have a 4K screen for a player, it may be hard to render some particle effects, and often you can just lower the resolution for specific things or for the whole screen just to meet the frames requirement. But again, it will cause problems. That's why DLSS and FSR comes in on modern GPUs. You just downsample everything, render everything in low resolution, but then AI kicks in on GPU and renders it in bigger resolution, which is not that noticeable, but still causes some bugs here and there. And also you can just simplify your shaders. You might not need multiple shadows, you might not need some specific lighting. You can just often disable lots of stuff and try not to use built-in default shaders if you find that it's a problem for you. Now, lighting. Again, long story, there are two main approaches to lighting, forward, deferred. Deferred is faster for lots of lights, but it might be harder to implement, may cause some glitches, but still think about it, try both cases. Then there is baking light. Before ray tracing, everyone had to bake light because you can't compute all the lighting, all the shadows for the whole level, every frame. It was too slow. So instead, you can just, you know that you have a level, you can pre-compute all the shadows all the lighting into those light maps. It will take maybe half an hour for a huge level, maybe even more. But for the player, it will take a really small time to render because the engine will just have to take the texture of the light, the texture of an object, and apply it together. For dynamic objects, there are so-called light probes and also reflection probes, which is a bunch of points you place around your level, or automatically again, and it will pre-compute the light in this specific point. So when you walk around, you will see that dynamic object will get lit based on the pre-computed. So it's an approximation, so it's not specific, but it often helps quite a lot. And fake shadows. You often don't need a huge detailed shadow of a player's gun. You might just want a gray blob underneath him, and that would be enough for lots of simple indie games, and if you don't aim to some AAA style. And transparency. A huge problem because in render pipeline it often renders opaque objects and then it goes to transparent ones. It has to sort them because transparent object behind another transparent objects. It's hard to compute. It's much more taxing on the GPU. It's really expensive, and you should try to avoid it as much as possible in general. Here's an example, for example, of an overdraw, which is, you can view it as a debug view in both Unreal and Unity. You can see that the lighter the point is, it means that more objects got rendered here. It's not related to transparency specifically, but you can see that in some cases, for example, like here, you rendered some lamp behind the wall, and you might want to disable it in some way because it still takes time to render. And also, it just transparent texture is an extra channel in texture, the alpha channel, so it's more data. Again, more data to pass to GPU will take more time. Now, how to avoid transparency? There are some, like one good way that I've seen in a lot of games. It's called dithering, which is basically you don't have actual transparency or translucency where you can see through the pixel. Instead, you render only half of the pixel, for example. Like here in Genshin, I moved my camera behind a tree, so this is tree leaves just shaking, and you can see that its black dots are leaves, and everything else is not rendered. It's faster because these leaves are technically an opaque object, kinda, because but you just discard some pixels and draw others, and if player moves quickly, he won't really notice that. So it's much faster. It's not that hard to implement. Plus, of course, there are plugins for that. So you might want to try that, especially on mobile devices, in VR. It's everywhere in VR and things like that. Another one is just optimize your special effects. Don't just throw particle effects with 1,000 particles for a fire or for smoke. You often need a graphics programmer who can design a mesh, specific mesh, design UV maps on it, and write a special shader, which is like a 3-line shader, but it still would be quite neat to on a player screen and wouldn't be as bad for GPU. For example, like here is just a simple mesh and a simple 3-line shader, and that's it. So here's a video from Asgard's Wrath from VR. Here you can see this dithering effect on a map table. I'm just moving my head around, and you can see that probably you can see that there are just black pixels and transparent pixels, and that's it. If you don't look too closely to that, you wouldn't even notice that, because you generally don't look into under the maps there. Specifically to Unity, sorry for everyone who is not using Unity, but canvases are terrible in Unity. It takes a lot of time to draw stuff, especially if it's transparent. The same overdraw happens. And the problem is that when something changes in your canvas, like you change a score or you have a timer that updates every frame, it basically redraws the whole canvas. It has to update a lot of stuff there. And there is a neat trick to optimize it. You can have one canvas which is with all the static elements, like I don't know, background elements, and you can have the dynamic elements with current timer. And so you just, to this object, you add a canvas element, and that's it. You don't have to do anything else. It would immediately be much faster. And another thing is often, for example, in scrolls, you can have 1,000 elements, and it will be slow if you try to add all of them together. You often have to fake it, so it's like a fake scroll where you only have visible elements loaded, and when the player swipes it, you just download new elements, load them into memory, unload all the elements, and that would be faster. Another thing that you might have some cameras in game, for example, where a player can come to a TV screen and look into some camera that renders another thing, and you have to remember that it's just as expensive as the main camera in most cases, and you have to try to optimize it. You can decrease the resolution because it's an in-game camera. It can be have really low resolution, really low quality, and of course try to disable it whenever possible. Network optimization. Again, this is a talk for another hour, so I'll just quickly go through it. Know the difference between TCP packets and UDP packets. If you are doing some first-person shooter, if you have to do something immediately, use UDP, but know that UDP packets will get lost at some point, sometimes, so you are not able to send important information like that. Try to batch packets. So if you are sending a bunch of data, it might be good to, if you are computing some data on one frame, it may be good to grab it all together and send it as one packet instead of sending a separate packet, because they have headers, they have extra data that will be sent, and it will be slower. You can minimize the size. Don't just send JSONs on every frame, please. Just use protobuf or anything that will be slower than that. Again, replicate only stuff that is needed. You don't have to replicate the fire particles from a fire on the ground if players don't care about it. But for example, you might want to try to replicate a smoke in a shooter game like in a Counter-Strike, because it's important what exactly a player sees there. And in Unreal, it's much better than in Unity. There is no multiplayer in Unity that works well, but in Unreal there is a relevancy and priority where you can configure each actor, how relevant it is to the player, so it will get less data if it's far away or behind the player. So often you can optimize it this way, especially for massive games like PUBG, Fortnite, whatever. You don't need to know about the players far away. You just cut them off, and even if they're not that far away but still not too close, don't send the packet every frame. Yeah, that's it. Thank you. If you have any questions, there's a link for the presentation that I've told you about, and Yeah, that's it.